Let's move or extend our one-way ANOVA to the two-way ANOVA. And once we start adding more factors, so remember one-way ANOVA, we had one factor or one grouping variable. So two-way ANOVAs have two factors or two grouping variables. Once we start adding these factors, we start calling these factorial designs. And so that's why I have that in parentheses there. Okay. So why do we want to consider a two-way ANOVA? Well, the one-way ANOVA has one factor that we use to explain the variation in our quantitative variable. And recall that we looked at eta squared, which is our sum of squares between groups, but divided by our total sum of squares. We talked about how that gives the proportion of variance in our quantitative variable that's explained by our factor. Well, there could be additional sources of variation that we haven't accounted for when we've conducted a one-way ANOVA. And so adding another factor could reduce our within group variability, our sum of squares within divided by our sum of squares total, which gave us the proportion of variance that is unexplained. Adding another variable, hence the two-way ANOVA or two-factor ANOVA, could decrease that unexplained error. So that's one way that we can, one reason why we want to consider a two-way ANOVA. And reducing this error or this unexplained variance will lead to a more powerful test. In addition to that, right, there might be another factor in some of our studies that actually moderates the relationship between our main factor and outcome variables from a one-way ANOVA, right? So when we're conducting a one-way ANOVA, especially when we're conducting an experiment, we want to see if that grouping variable, so manipulating those groups, actually have an impact on our outcome variable. So X in this diagram will be our independent variable, our grouping variable, and then Y, excuse me, will be our outcome variable. When I say that there may be another factor that moderates that relationship, there could be another factor, I'm calling Z here, such that the effect of our single factor in a one-way ANOVA, the effect of those different groups and whatever I'm treating or whatever treatment I may have in my experiment or whatnot, it may depend on the levels of another variable. And so one group may have higher means for one level of that variable Z, while another group of my variable X may have lower levels or lower means for different levels of that moderating variable Z. And so the two-way ANOVA allows us to see if there's some interactions between that moderator variable and our main factor. And this is another reason why we may want to consider a two-way ANOVA. So let's look at some examples and try to identify the variables in the study. Um, in this example, we have a random sample of 40 people that are put into one of four groups. Now, there are four groups, but the groups are going to be created by looking at two groupings. They are either going to be put on a diet 1 or diet 2, and they're either going to be in an exercise group or a sedentary group, right? And we're going to have combinations of all of those groups there. Our goal is to see whether the mean weight loss varies significantly by diet or weight loss. Sorry, by diet or exercise. And so I'm going to identify the variables, and then I'm going to be a little bit more specific because the way the groups are written here, it looks like I don't have any combinations of these variables, but we actually have combinations of these variables here. All right. So one of my groups is variable one. Sorry, one of my variables is variable one, which I'm calling type of diet because the individuals are going to be put in diet 1 or diet 2. The other one, of course, is the exercise level because they're going to be put into be assigned to receive exercise or be sedentary, right? And then my third variable here is weight loss. So one of the things that I really, really wanted to do here is to be able to identify that we have three variables in this study. Two of them are actually grouping variables, so those are our factors. So that variable one is factor one. Variable two is factor two. Those are our factors, our independent variables. And then our weight loss variable is our quantitative outcome, our dependent variable, right? But I want to make note here, diet one and diet two does not make two separate variables. It's a part of one variable, but that variable takes on two values. The same thing happens to the exercise or sedentary groupings. That doesn't make two variables, it's two values of a single exercise level variable, right? But in either case, what we're going to do in a study like this is we're going to assign individuals to combinations of these groups. All right. So, for instance, some individuals are going to get diet one with exercise. Some individuals are going to get diet two with exercise. Others are going to be assigned to diet one and be in the sedentary exercise group. And then the last group is for diet two with the level of exercise being sedentary. Those are the four groups here. And we're not looking at a diet one, a diet two separately from exercise or sedentary. We're looking at the combinations because we need to see if there's some moderation potentially going on, meaning, okay, your level of weight loss depends not only on just diet or just exercise, but maybe a combination of diet and exercise. That's the goal here. So, what types of statistical hypotheses are we going to use, right? Well, so far, I've identified that we have two factors in this study. When we had a one-way ANOVA, we had one factor. That means we had one hypothesis test, one test statistic, one p-value, all of that stuff with one factor. When we have a two-way ANOVA, we have two factors. So we're going to actually be conducting two hypothesis tests at least when we look at these two-way ANOVAs. And it says that each set of hypotheses are written in the same way that we would write the hypotheses in the one-way ANOVA, referencing the population means, either in words or symbols. Again, there may be multiple ways that you can do this. So let's go back to this example of the 40 people and getting assigned to some combination of the diet or exercise groupings, right? So remember I said that we're going to have two hypothesis tests. That means we have two sets of hypotheses, two null hypotheses, two alternative hypotheses, one for each factor. So I'm going to look at the factor type of diet first. Remember, it takes on the values diet 1 and diet 2. The null hypothesis is that those means are going to be equal in the population. Alternative hypothesis is that those means are not going to be equal. Now, I can write this easily in symbols because those groupings for the diet, there's only two groups there. So I can write this using symbols pretty easily. But I'm going to show you one way that we can write it in words. We can say that for our null hypothesis, there is no significant difference in population mean weight loss among the diet groups, right? That is one way. I'm sorry that I'm abbreviating here, but I'm not going to be able to fit everything on the screen. No significant difference in population mean weight loss among the diet groups. Another way to say that, since this is only two groups, I know that mu of diet 1 equals mu sub diet 2. Or I can say that all of the population means are equal between the diet groups. All right? So I've given you three different ways to write that single null hypothesis. Choose one. Choose one. You don't have to do all three ways anytime we're writing a null hypothesis. Since we're learning, I'm just giving you options here. The alternative hypothesis is that there is a significant difference, or that those means are not equal, or at least one population mean is unequal. Now, I wrote the at least one population mean is unequal to accommodate for cases where we may have a group, a variable with more than two groups, right? So that's why I say at least one population mean is unequal. Well, we only have two here, so kind of doesn't aligned there. But I did want to include this to match cases where we may have more than two groups. So that's my alternative hypothesis. At least one diet group population mean weight loss is significantly different from the others. All right, and we have a similar situation going for the exercise level, right? We had two values or two groupings. They'll be assigned partially to an exercise or sedentary, along with the other combination of the diet variables, right? But this null hypothesis focuses only on the exercise level variable. It says there is no significant difference in population mean weight loss among the exercise level groups, and at least one exercise level group population mean weight loss is significantly different from the others. All right, and then we can write those in symbols as well, or we can say all the population means are equal between the exercise level groups, and at least one of them is unequal. All right. Again, we're going to have a null and alternative, very similar to the one-way ANOVA. All right. When we're testing our separate hypotheses here, that test of the type of diet variable, that factor, it determines if weight loss between diets averaged over both exercise level groups is significantly different. Meaning it's not looking at which exercise level group you're in. I'm testing whether those means are different for the two diet groups, right? That's what I'm doing when I'm testing type of diet as a factor. When I test exercise level as a factor, I'm determining if weight loss between exercise levels average over both diet groups is significantly different. So it's not like I'm ignoring the diet group and just looking at the means for the exercise level groups, right, on weight loss. So that's what those tests are doing. But that is not necessarily all that we need when we're doing these combinations, because these two, they're just testing type of diet and exercise level respectively. But we want to also look at the combination of type of diet and exercise level. So these two hypotheses are not enough for us to get there. That's the point I'm trying to get at here. And I have a question here. Could we determine if weight loss depends on certain combinations of diet and exercise level? When I get the F statistic, the p-value, I make my rejection decision and I draw conclusions on both of those tests. By the way, these tests are sometimes called main effects because I'm looking at that variable mainly by itself. So it's a main effect. I'm looking at that variable only when I do this test. And then when I go over here to exercise level, these hypotheses are just about those main effects on our outcome variable. When I want to look at the combinations of those two, this is when we have what we call interaction effects. An interaction effect occurs when the effect of one independent variable depends on the value or the level of another independent variable, right? So I may have a significant difference between diet 1 and diet 2, but when I have an interaction, diet 1 may be much more effective under the exercise group compared to the sedentary group, right? That's when we start to see some interaction effects. Now, there are some studies where I cannot test for an interaction effect. So there are some data requirements. One of the data requirements, or the main data requirement, is that we need replicates in each group. All that means is that we need multiple individuals in our study in each group. Sometimes we have very small sample size study where they put one person in this group, one person in the second group, one person in the third group, and one person in the fourth group, right? That's a very small study. There's no replication in there because I have one individual in each of those groups. That means I can't estimate a sample mean. I can't estimate a sample mean in each of those groups. I need replicates, meaning a small sample of observations in each of those groups in order for me to test for an interaction effect. All right. Now, I don't have to necessarily remember that because the statistical software is going to let me know if I have my data, this data requirement met. And you're going to see when we look at some examples what it would look like if the data is not met and what error JAS gives us, which will not allow us to run a two-way ANOVA with interaction events. All right. So when we want to actually determine if there is an interaction effect, right? We're going to look descriptively first, and then I'm going to tell you about the hypotheses. When I want to determine if there's some evidence of an interaction effect in my sample data, that's coming from descriptive statistics, then we can explore what we call an interaction plot. This is an example of what an interaction plot looks like. One of my grouping variables are going to be on my horizontal axis, and the other factor is going to have its values as the separate lines in this interaction plot, right? So I see I have diet on my horizontal axis, and then the exercise level variable, its values as the separate lines in my interactive plot. My vertical axis is going to be my quantitative variable. Now, if I look at this plot here, there is some evidence of an interaction. And the evidence comes by way of determining whether we have parallel lines or non-parallel lines. Some people say skewed lines if it's non-parallel. If the lines are parallel, then there is likely no interaction. There's likely no interaction, all right? But if the lines are parallel, or especially if they're crossing or intersecting, then there is likely a potential interaction. But again, this is just looking at our data descriptively, just looking at it descriptively. All right, we would have to do a hypothesis test to see if it's a true interaction effect or it's highly likely beyond chance that is an interaction effect. That's what we'll use our hypothesis test for. So look for a non-parallel line to say that you have an interaction effect or evidence of it. Hypothesis test is going to give you more rigorous information about that. Well, if we ever test for an interaction effect, we have to have hypotheses. So for those two, looking at those, the hypothesis test for those two variables separately, my two factors separately, those are the main effects. I have those hypotheses, those p-values, those f-statistics, those decisions, and those conclusions. We're going to add another hypothesis test to test for the interaction effects. My null hypothesis is that there is no significant interaction effect between factor 1 and factor 2 in the population. Remember, we can write our null hypothesis in words. We can also represent it in symbols. Now, this is the thing. Remember, I said that when you have no interaction, your lines are parallel. Our null hypothesis, our alternative hypothesis, any hypothesis test is all about population means because we have a quantitative variable here. So if these lines are parallel, that means I'm going to show you how this null hypothesis is written. I have mu diet 1 exercise. That's this here, this point here. Mu diet 2 exercise. That's this point here. So if I take, and I know I'm doing this from a descriptive chart, but I'm just using this as an example to show us. Mu sub diet 2 exercise, this distance, this subtraction here, sort of represents the distance, the vertical distance between these two points here. This point here and this point here. So think of drawing a right triangle. And I'm going to try to do this using my mouse, sorry. So if I were to draw right, oh, this is not working. I guess I will not be doing that. All right. Well, if you can follow my mouse, I'm so sorry. Oh, this is nice. Um, Muse of D1 exercise minus Muse of D2 exercise. If I ignore the sign of that difference, it would represent the distance for the y values of these 2 points here, right? If there is no interaction, that means I have parallel lines. So if I were to think if this line right here were parallel, then the distance, if it were parallel, the line would look like this. I hope you're following the screen here. And the difference between those two y values of those points would have to be equal, right? So this is a clever way of basically writing that those two lines are parallel from our interaction plot. Now I know that again the interaction plot is about sample data, but this is the way to do it. So mu sub diet 1 sedentary, which is here, minus mu diet 2 sedentary. If it were parallel, it would be up here. That subtraction would be equal. So this is two way of saying there is no interaction. The lines would be parallel. That's my null hypothesis. My alternative hypothesis is that there is a significant interaction effect between factor 1 and factor 2 in the population, and I can write my alternative hypotheses this way. All right. Now, this means that when we conduct two Way ANOVAs, we now have three F statistics, three p values, three decisions, and three conclusions. All right, for any of the examples where we do have the replications in each of the combinations of groups. And when there is a significant interaction, there is some evidence that one variable is moderating the effect on the outcomes. All right. And so we're going to look at some specific examples of plugging these values into JASP, or looking at some examples of applying those examples to JASP to walk us through full analyses of conducting the two-way ANOVA. We'll do that in our next video.